Don't let him trip on us.
I want things to happen. Is there two things happening today? Like those two.
Good morning. Welcome to our science seminar for today. It's a real pleasure to have with us DavidLary from University of Texas, Dallas. David is here with his son Matthew. So introduce yourself to Matthew and David. Matthew is looking for an engineering school to go to. He's in high school now. So you can give him the real scoop on Laterno as to whether to come here or not after the seminar.
It's weather to come here.
Whether when to come here, which major to be in as a chemistry major. All right. So David didn't go to Laterno University. He got his undergraduate bachelor's in science degree in both physics and chemistry from King's College in London. And then he wanted to get a PhD from the University of Cambridge in computer modeling of the atmosphere. And since then, oh, and by the way, he got honors in both chemistry and physics degrees when he was over there at King's College. Since then, he's been a lot of different places. He's worked for a lot of very interesting things. Okay? Currently, he's at UT Dallas as a professor of physics, but he's also an adjunct professor in a number of other different areas, including electrical engineering and all kinds of stuff. He's got stuff on his resume here from NASA Goddard Flight Place and Southern Methodist and Baylor and all kinds of places where he's been collaborating with and working with. And it's really exciting just looking through the slides that he sent me about his talk, about all the cool stuff he's going to be talking to you about today. So, there's going to be a great talk today, and I hope that you'll appreciate it. And I want to remind you that we have lunch with the speaker after the seminar, and if you have further questions and you want to join us for lunch, we'll be in the Joyce Room of the Corner Cafe. And if you're a student and you don't have a meal plan, I can cover your cost for your meal. So if you're going to lunch after the seminar, come and join. Otherwise, let's give a big warm welcome.
Thank you so much for having me. Can you hear me all right?
Yes.
Yeah. So at any point you can interrupt. So I hope that I'll be able to both inspire you and challenge you. So what you see right here is a simulated event that we all hope we will never be in. But actually, if you strive for excellence in your studies and be the very best at what you can, at what you're doing, maybe you'll help people keep out of the way of an event like this. This is a simulated bioterrorism attack. So what we're trying to do is build holistic observing systems from the planetary scale, from satellites. So I've been doing that with NASA and the European Space Agency, and now to the street level. So none of this is about Big Brother watching you. It's about if you or someone you love or someone in the country you love is in the way of something like that, you want to give them the biggest heads up possible so they can get out as quickly as possible. So everything we do is focused on preemptive human protection. So I'm going to show you a set of examples of these, but I have to warn you, I get a bit carried away, so in case I don't get to the end, I wanted to give you up front the range of things we're doing. And so much of this is being done together with graduate students at UT Dallas. And I can see from the maker projects and so on that you guys are doing, I think it could be right up the street of many of you. So if you've never considered graduate study, maybe you want to give it a second thought, because for me it opened a gateway for a really exciting ride. And if you can make a difference, you can serve society, there's nothing more satisfying. So what we're doing is we're now building street-level sensors. So the EPA has had its own trials, I guess, recently. And so for the Dallas area, which is the largest inland metropolitan area in the country, 7.5 million people, growing by 1,000 1,000 people a day, 500 being born, 500 moving in, has 3 sensors for airborne particulates for the entire 7.5 million people, which is an area the size, which is bigger than a New England state like Rhode Island. Okay, so we hope by the end of next year we'll have deployed 150 sensors, and we use the whole maker concept. We basically turn El Cheapo sensors into high-end sensors by calibrating them against reference instruments using machine learning. So the students have been involved in the designing, building, calibrating, and deploying of the sensors. We also involve high school students, so it's everything from high school to graduate students involved in this. We're also building robot systems. So yesterday I was in the oldest proving ground in the country, Edgewood in Maryland, and we're preparing for a kind of nerve-wracking demonstration in a month's time where we'll have coordinated robots. There'll be an aerial robot flying over it carrying a hyperspectral imager. So when you take a picture with your phone on your camera, as you probably know, you have 3 images, a red one and a green one and a blue one. You combine them, you get a color image. So for every pixel you have 3 pieces of information. But now imagine you have something like 400 wavelengths, or maybe 1,000 wavelengths. So for every pixel you have a spectra. You can turn that spectra into a lot of useful information. If you're in the agricultural context, it could be what the crops are, what is the yield likely to be, is there an infestation, like as a factoid, Lay's chips, you've probably all eaten Lay's chips, right? So they have these massive fields of potatoes, but there's some beetles that love to eat potatoes. And so if there's an infestation on the edge of a field from one of these, they will start chomping away. It will immediately stress the plant out, and you can see that in the hyperspectral signature that you could get by flying over the top in an aerial vehicle. So if you catch it right then, you can deal with the beetles before they've infected hundreds of acres. You can also have like optimum planning of when are you going to harvest this. And that can be important because if it's going to rain and you have a crop of tomatoes, when it rains, the harvester will like sink into the ground, and instead of having prime tomatoes, they could be canned tomatoes, so it could have a big impact on the bottom line. Or what we're trying to do, and what we've already done from space, is we have coordinated robots of the aerial vehicle and the robotic boat. So the robotic boat is measuring everything in the water with a mass spectrometer, a set of fluorometers, and so on. And the aerial vehicle flies directly over the top of this. And we have the hyperspectral signature, and we use machine learning to map what we see remotely to what's actually in the water. So we might never have seen that signature before. As long as there's a chromophore, like as long as there's an absorption that we can see, we can create that mapping, and then we can get a really large area view. So supposing now it's Hurricane Harvey all over again. So the Gulf Coast, you have the hurricane coming towards you. You can see that in the satellites with the simulations. You know pretty much where the landfall is going to be. But then the landfall happened just where all the chemical industries were. So now this hurricane is a major natural disaster because you have toxic chemicals go into the water. So there was one neighborhood surrounded on 3 sides by water. This water was now inundated with volatile organic compounds, really things you don't want to be breathing. They started having severe respiratory issues. But it was a socio-economically challenged community. They're struggling to even make their mortgage payment, let alone pay for some environmental remediation. So our goal is our robotic system can go into a place like that, characterize exactly what's there for helping the cleanup or wearing protective clothing, whether it's for a hurricane or some lunatic lets off a chemical weapon or whatever it is. It's really helpful to keep people out of harm's way. So that's the goal of everything we are trying to do. And it turns out that dense urban environments, which is the fancy term they use for mega cities, are becoming more and more the target for all kinds of nefarious things. So this is a double use thing. It's for the everyday air quality that we all live in. And so let me just throw out an example there of why this is relevant. So the leading cause of poor learning outcomes in high schools is absenteeism. The leading cause of absenteeism is asthma. The leading trigger for asthma is airborne pollution or pollen. If you exercise strenuously in the presence of high pollution, you are more likely to have an asthma event. So imagine now that instead of the coach just deciding where practice is going to be, if they have a sensor like the ones we're building, giving you the actual size distribution of airborne particulates, pollen and mold, they can make a data-driven decision on where practice should be. That could make the difference between how many asthma attacks those students have, and then that can have a knock-on effect for their learning outcomes, but also the schools don't get paid if the student is absent. So it's like a win-win virtuous cycle. Everybody comes out a bit better. So the goal behind all of this for preemptive human protection is data-driven decisions. If we don't have the sensors, we don't know. So I'll just throw some of these out there at the beginning because I'm worried I won't get through all the slides. So another thing is you might see a news headline that says, poor air quality makes you dumb, right? So, but how dumb is dumb? I mean, we know people kind of sniff all kinds of things and that gives them a high. But supposing now it's the 3 largest cement factories in the country, which we have in Dallas, which I'm all for people making a profit, but they try and make an extra profit by being a furnace for hire. But if you're now burning car fluff, and so that's everything that is a metal basically, you can now be releasing neurotoxins into the environment that the community typically living right next to that cement plant is again a similar one to the Houston one I was mentioning, which they don't have the resources to do something. So we can be servants of society by actually helping identify and keep people out of harm's way. It's like we have the concept of canaries dying down a coal mine. So my goal is that no canaries need to die. Okay, or no humans need to unnecessarily die. Like if we can sense things, we can stay out of harm's way. Okay, so yeah. So let me show you a schematic of this big picture. So apart from the robotic submarine, we're doing all of these like right now. So I started with global satellite sentinels and simulation. And that can be very useful because you get the large-scale picture. So, for example, with the Hurricane Harvey example, long before it made landfall, you can see those global weather systems coming in. And in fact, interesting thing, the cyclogenesis region for most of the hurricanes that hit the US is off of the west coast of Africa. And if we ever get to it later, we also see that's a region which is a lot of dust sources occur there. So I don't know how much those are related, but it's kind of intriguing to see the same. So we can come down to a slightly smaller scale with the aerial vehicle. So right now, the aerial vehicle that is carrying our hyperspectral camera can take a payload of 35 pounds, which is pretty awesome. It was designed for filming movies, so it's very low vibration. If any of you have seen the movie Venom, they used it for filming that movie Venom. If you want to check it out, it's called a FreeFly Alta X. It's made in Washington State. And so this platform is vibration isolated, really low vibration, so that's important for getting good images from the hyperspectral camera. So this can do a large area survey, so it can be for water, it can be for land, it can be for crops, all kinds of things. So right now we just have the hyperspectral camera, but we also want to have a synthetic aperture radar. Now that's very useful, say, for another thing we all heard about, Deepwater Horizon. So when you put oil onto the water, you actually change the surface tension, so you change the wave heights. So synthetic aperture radar can pick up things like that, but it can also pick up change detection. So supposing now you're in a place where somebody's burying landmines, you fly over, you get the exact terrain, you then fly over again, if there's as much as a footprint on that surface, a tire track, you can see it. So if somebody's been digging a tunnel and they're settling, you'll see that too. If you have a salt dome like they have down in Florida under the ground, and then you groundwater coming through there can erode that, especially if you have, say, a lot of fracking going on and you're pumping groundwater, it can dissolve that salt dome, it can collapse, and then you get a sinkhole. So changes in the surface like that you can pick up. So we're also building the sensors, as mentioned, across the city. Yesterday, have you seen the YouTube videos about the Boston Dynamics big dog? Okay, so the guy who was the grandfather of that was a professor at the University of Philadelphia. So some of his students, graduate students, it's really cool to do a graduate degree, went off and did Boston Dynamics, and another group of them built Ghost Robotics. So the difference between these two companies is that Ghost Robotics, where I was visiting yesterday, they really do all their sensing through their motors. So supposing you come up the stairs or you stub your toe, you feel through your feet that you stubbed your toe. All right? So even if we were blindfolded, maybe not so gracefully and maybe a bit slower, we could probably work our way up those steps just through our sensing through our feet. So that's the idea of what they're doing. So the robot that we were looking at yesterday and will be part of our demo of the 3 coordinated robots I mentioned has 12 motors. It does all its sensing through the motors. So they can then add the radar, the LiDAR, the cameras, and they do. That makes it more graceful, but the basic sensing is through that. So it means they can build them lighter and cheaper and deploy them more rapidly. So that's often very important. So we also, this is our ground survey vehicle. So this little granny car electric bolt here actually is packed in the back with sensors that are reference sensors on the roof too. And besides, the granny has quite a go in here. It's 550 horsepower, so that's pretty... Anyway, you don't drag race with a bolt. And so this is our robotic boat. It was built for us in Norway. It's the best in its class. It can be autonomous for 20 hours. And so we actually use exactly the same flight plan as we have for the aerial vehicle, so our boat can underfly it. Now, in case you wonder why am I going on about that. So the global data products that people like NASA and the European Space Agency and now other space agencies build, and I know because I was involved with building these, for the global ocean products, they typically had 18,000 training data points. And these data points would be happenstance overpasses between a satellite, seeing things remotely from space at 600 kilometers in orbit, from an ocean-going scientific cruise. Now, in case you get excited and think, I like the sound of that ocean-going cruise, this is not a Carnival or Viking or Holland America cruise. It is hard work, sweaty, stinky, rather wet. And so over a month-long ship cruise, they would get like 10 happenstance overpasses between the satellite and the water measurements. So that's what inspired me to have the team of the aerial vehicle and this. So we have a precisely coordinated overpass every second. So in 1 minute, we get more overpasses than this multi-million-dollar cruise acquired in a month. So, albeit that we then now need to sample many locations, we have an easy-to-deploy autonomous platform at a fraction of the cost of those other things that could be deployed anywhere. So that's kind of what excites me. So apart from the car and the satellite, all of these things can be packed up into cases and deployed anywhere on the planet. So whether that's for cities or the military, the idea is, in all of it, is to keep people out of harm's way. So, and then, if any of you have done this type of thing, you'll begin to realize it's one thing to have your sensor, It's another thing to have the delivery vehicle, but to have loads of them working together, that's where the pain really comes. So the twinkle in my eye, the vision I have, is to have an off-the-shelf suite of systems that you can just mix and match like a Lego kit. These together, they'll just work together, have the machine learning and other things built into the system so it can be ready to go for a wide variety of applications. The submarine would be cool, but that's still dreaming about that. Okay, so let's just take a moment to say, why do we care about this? So I heard someone suggest that maybe this is about Big Brother snooping. I abhor that type of thing. I don't want to snoop on anyone. I want to keep people out of harm's way. And this is an example for that. So in the US, there's about 50 million of us Americans that have allergic diseases. Of the 50 million that have allergic diseases, about 26 million have asthma. So I don't know if any of you have asthma. An asthma event is very unpleasant, something to be avoided. But every day, about 44,000 people, every day of every year in the US, 44,000 people will have an asthma attack. 36,000 kids will miss school, as you can see, but it's not just kids. 27,000 adults will miss work. Of those people, 4,700 will go to the ER. It'll be a bad enough asthma event for that. 1,200 will actually then get admitted. Now, that was a very bad asthma attack. And unfortunately, on average, 9 die. So I'm not saying we can save all of these, but a preemptive alert could be really helpful. Or maybe now it's not as extreme as that. So on the one end, it could be a veteran with COPD. But at the other end, maybe you are much younger, you don't have any of these issues, and I hope it stays that way all your life. But supposing you want to decide where to go for a run, or a bike ride, or whatever. So we're so familiar with our phones now, we have the shortest distance to wherever we're going. Or maybe the least time if it's a traffic issue. But how about the least polluted route? All right? So, or now you've got a bit older and you've got your first grandchild. I mean, your own kids is one thing, but your grandkids, that's even more amazing. So you want to go for a walk with your grandkids, and if you think about it, little Johnny or Susie in the walker there, in the stroller, they're about tailpipe height, right? So if you go for a walk with them, you could be gassing them needlessly, right? So if you can figure out with public information, all open data, which is what we're doing, open platforms, open data, where the least polluted route is, you'll have a much nicer walk or jog, because it's not nice to smell the stink of whatever. And also you won't have gassed Johnny or Susie in the stroller. So actually it's easy to overlook the significance of this on a global scale. So pretty much every year the World Health Organization come out with an evaluation, and so this is from a few years back, in 2012. They estimate that 7 million people globally die because of pollution. So I'm not saying this to be scaremongered, far from it. I'm saying this is a big issue and we can actually do something about it. Like, we can see each other in this room because we've been blessed with eyes that we can see each other. But there's an elephant in the room that unless we have the sensors for it, we actually don't know the elephant in the room. But it doesn't mean it's not there, and it doesn't mean that the elephant isn't having a major role. So, if in any other context we were to hear 7 million deaths, that would be shock horror, like mass genocide. We'd all be doing something about it. But when it comes to pollution, we seem to somehow ignore it. So, or it's all too easy to ignore it. But I think we should hold ourselves accountable and society accountable to leave the world a better place than we found it. So, we're now beginning to touch on one of the big challenges. So when we say go to a physics class or a chemistry class, we often reduce our system to one that is tractable to understand. So let's take a really simple one. Say we're doing mechanics in introductory physics and we have a projectile. Okay, so the simplest thing, we just have the angle of the projectile, we have Newton's laws, and we ignore wind resistance. Not because wind resistance isn't there, but it just makes the math simpler. And then we take it up a notch and we do the wind resistance, and we get progressively better. But now think of the system we're dealing about here, all right? We're each humans. We're this amazing system of all interconnecting parts, our sensing, our immune system, we're awesomely created beings. And we don't really understand how the pollution is affecting us. So if you actually look at, I've done this, I looked at every ER admission for an entire year for the state of Maryland when I worked at NASA Goddard, so I partnered with the nursing school. And most of those ER admissions were from the city of Baltimore, because that's a major population center there. And so I had every single ICD code, so I don't know if that means anything to you, but I hope you never have to go to the ER, but if ever you do, or someone you love does, you will be classified by a primary, maybe a secondary, and a tertiary ICD code. So did I have a broken arm? Was it a heart attack? Whatever it was, it gets a code. So I looked at all those codes, I counted them for the entire area on a daily basis, and I related that to the environmental conditions. So you had some things that were kind of obvious, like the asthma that I was talking about, but what was interesting about that is normally when you read the literature about the asthma, it will say ozone and particulates are the most important things. So they do have a role, but actually a couple of other things were more important and were not mentioned in the literature at all, which is why I'm saying the pervasive sensing is really important. So carbon monoxide was even better related to the asthma admissions, and the best one of all was an inverse relationship to temperature, actually. The colder it got, the more asthma admissions. So I don't know if any of you have asthma, but if it's a cold day, you're likely to have more issues with asthma, and that showed up with the ER admissions. So that's interesting and helpful, but there were some other conditions that I didn't expect to see. So if you looked at unspecified schizophrenia, not the other types of schizophrenia, because there was ICD codes for all of them, the unspecified one, they were tracking really well with airborne particulates, way better than the asthma. So I don't know the causal relationship. All I'm saying is there was a really strong association there. So what I'm trying to get at is there's a lot going on that we don't understand. But if we have the data that's robust on the environment, if we have the health outcome data that's robust, we can actually use machine learning to try and bring the stuff together to help us identify associations and maybe then go the next level to do something about them. So, if you think about these health outcomes, we're now sequencing entire genomes. What a couple of decades ago was unheard of is now routine and off the shelf. We have unprecedented amounts of electronic health records. Initially this was just for the military, now it's for the general public. The kind of spanner in the works there is there are multiple electronic health record systems, and they're deliberately, by the vendors, not cross-compatible. So that's just life. And then we have the environmental context. So we have these three parts of the jigsaw, each of which are massive data sets, and we don't have a theory that describes them. But if we use machine learning, we can actually bring these things together to try and help us get some insight. So let's just delve into this a little more. So these airborne particulates I've been talking about, I don't know if you have a sense of their size, so let me help address that. So on the left, obviously greatly enlarged, you have a human hair, which is about 70 microns across. Where micron, of course, is a micrometer. And then that's a grain of sand, typically about 50 microns. So two of the criterion pollutants that the EPA in the US and other environment agencies track typically are called PM10 and PM2.5. So the PM just stands for particulate matter. So it's deliberately not specific. It's anything, any bits in the air. It could be from soot, it could be from sand, you know, you name it, it could be it. It's about the size. And then PM2.5 is 2.5 microns or less. So these the smaller you go, in fact, the more likely they are to have health impacts. And that can be not just, as we've said, for respiratory-related things, or, as I mentioned, unspecified schizophrenia, even reproductive health, low birth weight. It's like there's hundreds of conditions that have been shown to really be drastically affected by this. So, what we're actually trying to count are the numbers of these really tiny particles. So for the PM2.5, you can see you can have 4 of those across a PM10 particle, and you can have 7 of those across a human hair. So these are so tiny that they easily get past the filter hairs in our nose, deep down into our lungs, and the smallest ones can even cross the barrier of the lungs and get in the bloodstream. So, you're getting the picture. This is pretty important probably to measure, and that brings us back to the earlier comment. So how are we going to measure these? So typically they're from instruments like this that, depending on their configuration and how many things we're sensing, will vary between $100,000 and $1 million. So I spent several years of my life, maybe it's sad, I don't know, bringing together as many of these observations as I could. So every little red dot outlined in black, which are those blotches across here, is a site measuring these annually. Now, to get the US ones, that was fine because they're all in a single database, but to get them for the rest of the planet, that was a bit more challenging. So, for example, the first ones for China, you might remember a few years back, there was the Olympics in Beijing. And so they cleaned up their air pollution beforehand, but that was largely because the American embassies in China installed instruments like this, and the only way they were disseminating them were tweeting that data. So I had to harvest the tweets, and then for many of these other places, that was really challenging. So what you have on here is about 8,000 sites in more than 55 countries measuring this hourly. Now, the simple takeaway from this is there are large fractions of the planet with no observations, all right? So take South America, there's large bits of that, or Africa, it's pretty much just in Johannesburg, just above my finger there. So what the idea was, can we bring together ubiquitously available data from things like satellites that are measuring the entire planet globally, and meteorology with the in situ data that we're getting either from those sensors. So this is the typical instrument measuring pollen data, balloons, aerial vehicles. So some of these are pretty large. You know, we've all heard the thing, how many ways are there to make a light bulb? There's loads of ways that don't work until you find the one that does. So I tried like 400 different incarnations of this, and this was just one of them. So what you see here is a list of the parameters that I fed into my machine learning, characterizing different parts of the environment, and I was using them to try and estimate the abundance of the airborne particulates. And in the end, actually, I was able to do a really good job. So this involved 10 terabytes of data. So the regular home internet connection right now in the US is of the order of 10 megabits per second. If you happen to have things like Google Fiber or Fios, maybe you can be up to close to a gigabit a second. Or if you're in the most privileged in the Western Hemisphere, within a 9-county region of Chattanooga, Tennessee, which is kind of surprising, you have 10 gigabits per second upload and download. All right? But for most of us, that's not the case. So at 10 megabits per second, that is 184 days to download that 24/7, assuming your connection doesn't go down, which is probably not going to happen. But so that's a large data set. So why am I going into that detail? I'm going into that detail when that type of volume of data blows our mind. It's actually not a problem for the machine learning. And machine learning can be very helpful. I've been grateful to use it for like 25 years now. And it can give our data a voice. It can help us get insights that can be tremendously useful. Now, we're going to if I go into all the things in this plot, we'll probably run out of time, so I'll just choose 2. So this here is the Badeli Depression in Chad. It's a dried up inland sea which has very unique sediment. It's fossilized diatoms from a very old inland lake. And on average, it's an ideal holiday destination. There's 100 days a year of a sandstorm. Okay? So you're always almost guaranteed to get one if you're going in search of a sandstorm. And 90% of the mineral dust that reaches the Amazon rainforest comes from this one location. Now, some of the satellites that NASA has, for example, one called Calypso, with a joint mission between the French space agency CNES and NASA, it basically has a LiDAR, which is a light radar, continually pulsing a laser beam, and it uses that, it looks at the reflected signal and gives you a vertical profile of the aerosols and clouds and stuff in the air. So you can actually see this plume of dust coming from there, taking about 2 weeks and ending up at the Amazon rainforest. So you can find in the Amazon the fossilized diatoms that came from this one unique sediment in Chad. So that's kind of interesting. But the next one, sorry, I'm not tall enough, just up there. So I don't know, do you know what the Taklamakan looks like? So if you just go left a bit, there's the Aral Sea. So the life expectancy next to the Aral Sea is a shocking 27 years. And so this is another example of why airborne, the composition of the environment can be important. So you might ask, why is the life expectancy 27 years? Well, it all started out very nice. In Uzbekistan, they have cotton fields. They wanted to irrigate those cotton fields by taking water from the Aral Sea. So they built some canals. Unfortunately, they weren't very careful when they built them, and they were very leaky. And in the process, they drained the Aral Sea. Okay? So that's unfortunate. You can go to Wikipedia and you'll see the time sequence of that. Fortunately, it's beginning to recover. But the spanner in the works was, in the middle of the Aral Sea was an island. And on that island, it was deemed an ideal place for testing biological weapons, like anthrax. So there was all this going on in this island. The idea is out of the way, nobody gets to it, which is great. But then the Aral Sea was dried out, and now it became a dust bowl, an anthrax-type dust bowl. And so the life expectancy is 27 years. So that's very sad, but it's true. So this kind of thing, you can begin to see it is actually relevant, and we can be servants of society by constructing this type of thing to help keep people out of harm's way. So you might say, well, how well did our machine learning system do? So these are some of the pictures. I said the $100,000 to $1 million installations. So every color-filled circle in this picture is an observation from one of these. The background color is the result from our machine learning to take the remote sense satellite data, the meteorology, the population density, take out hourly data from 8,000 sites in 55 countries over 2 decades, and use the machine learning to learn the mapping from what's ubiquitously available to what we really wanted to know. So it actually does a pretty good job, except in a few locations. Again, I'm not tall enough, so if you just follow up the line up there, you'll see there's a place where there's a red dot over a blue background. Now, why is that happening? Well, this looks like a fine resolution from the background, but actually the pixel size is 10 kilometers. So on a global scale, that's a small pixel. On the scale of you and me, that's pretty massive. So imagine now, have you ever gone past a chimney stack and you see the plume coming out of that? So you get variability over a smaller scale than 10 kilometers. So if you have a 10 kilometer by 10 kilometer average, that's 100 square kilometers, and you have a massive source in the middle of it, you're not really going to necessarily do a very good job of depicting that fine scale from the gross average. So we wanted to set out, answer the question, what scale do we really need to be measuring to accurately characterize neighborhood scale health? So it turns out, so we drove around a graduate student did, a 10 by 10 kilometer square every day for pretty much 3 months. That was part of his PhD. And he was measuring every second. So every second he got the full size distribution of these airborne particulates. So that turned out, given the speed limit, 1 measurement per second is pretty much less than a meter resolution. So we then looked at, we expanded the spatial scale to see how a given separation, how values a given separation apart were correlated. And it turns out that we need to be making a measurement every half a kilometer to every 7 kilometers, depending on the synoptic situation. Now, if these things are $100,000 to $1 million, like, good luck with that. So that's why we went to this hierarchy of standards with El Cheapo sensors calibrated against higher end ones and being traceable. So now we're actually deploying those. So I'm sure you've all heard of machine learning, but in case you haven't, or you don't really know what it is, it's the idea of giving computers the ability to learn without explicitly programming. So you learn by example. So for machine learning, there are two key ingredients: an algorithm to learn by example and the data to actually learn from. So you can have the world's best algorithm for your problem, but if you don't have a good representative data set, it's not going to perform well. You need both of them. And then for a problem like this, after you've done that, you always want to validate it against an independent data set to check how well you're doing. So I'm running out of time. So briefly, so we're also trying to measure airborne pollen from weather radar data. So that kind of thing, why would we do that? But we're all familiar again on probably our mobile phones, the weather radar. Like today, I looked at it coming in, it was raining. And so the radar signal that goes out is reflected from those airborne droplets, snow, ice, or so on. But it will reflect from anything. So it reflects from pollen. In fact, from the 9/11, the smoke plume that came out of the Twin Towers, you could see that in weather radars. Often in the weather systems in front of a front, you will often move insects, and you can see the reflectivity from insects in front of it. So we're also now trying to see airborne pollen and particulates in it. So it seems to be promising. So this is a picture of some of the small sensors we're using. So there's a laser inside here. It's about this size by this size by this size. So when I first came to UTD 10 years ago, the cheapest way to measure the size distribution of these particles was something like $20,000 and weighed 20 pounds. So now these are coming down to about $300 and they're really light. So, and then we calibrate them against a reference with the machine learning. So we can deploy these at scale. And so this is one of those drives that I wanted mentioned that the student was doing. So the color-filled circles that you see on this Google map are relating to the abundance of those particles. Blue is low, red is high. So if any of you know Dallas, this is Route 75 running up the middle, and you notice there's a red blob right next to 75. So that's where the student stopped at some traffic lights. So his engine was idling, all the other engines were idling. Then the lights change, everybody steps on the gas at the same time, and that's when the engines produce the most particulates. And then you can see as they come up to their cruising speed, it goes from the red through the green and back down to the blue. So what is ubiquitous in all of these observations is spatial change and temporal change. So it's critical that we have sensors measuring in real time. So typically the EPA sensors will be very high end, but they will only have a time resolution of an hour with a latency of 2 hours. So they give it to you at the quickest is 2 hours after the event. So if you're now the school coach, that's a bit late because a lot can happen in that time. But here you see our first day of 24/7 measurement. So every vertical colored stripe is 10 seconds wide. This axis is the size, and the color is the log of how many particles of that size were counted in that 10 seconds. So the red, these red things will be more than 100 particles were counted in that 10 seconds. So what you notice is the bigger the particles get, the smaller the abundance, because they simply fall out. All right? But these smallest ones, they stay lofted much like air molecules. They just bounce around. They have a long resonance time. So if you take an hour window, you see a lot happens in an hour. We are throwing away a lot of information by not recording more frequently. So one of our senior design projects going on right now is we're streaming live all of our data onto a map. We overlay the wind arrows, which looks pretty cool actually, and the weather radar. So right now for the 7.5 million people in Dallas, there's just 3 sensors, but we hope by the end of next year there'll be more than 150. So we're really excited about that. So this is just a and the last one, we can actually measure airborne mold, which normally the UK don't measure. So this is our cascade of standards, $100,000 to like $2,000 to like $200. So we calibrate them using machine learning. So this is a picture of our car, which has all the reference instruments in it, and these are some of the earlier versions that we deploy across the street. So we get hundreds of thousands of coincident records that we use to calibrate the low-cost sensors. Now, I could go into more of that, but I'm running out of time, so let me show you some of the other stuff, which is cool. We've probably all seen the movie Avatar. So the avatar is you in a game, but imagine now you have a character. So the character, so Ben is a virtual character. You could change the gender, the